x squared, or you can put in x squared over 18. Put that on your y2. So when your y equals, just go down to your second one, and you can put your x squared over 18. And we're on the same viewing window. Wait a minute, did mine just not work? Did yours work? Mine doesn't look any different.
It's like the exact same.
Oh, it looks like the exact same. Here's the way that you can tell whether yours worked or not. Go back to your y equals on your second one. On your second equation, go to the left of the y equals with your arrow buttons and press enter until you see the thick line. All right, then move to the right of that so that I'll see my first equation graphed in a skinny line, the second one graphed in a thick line. And that'll let us see. Mine just didn't look like there was any difference. All right, you ready for graphing? All right, so when we graph, here comes our circle, if that's a circular lens, and then yes, the parabola seems to be right smack on top of it. There doesn't seem to be any difference, really.
Mine is different. Yeah, same.
All right, so you've got a slightly different window. We're going to, what does your window say? Because that's where we're going to go next.
Negative 10, 10, 1, negative 10, 10.
All right, so let's try that, guys. Let's go from negative 10 to 10. I'm glad you experimented with something else. And from 1 to 10, or 0 to 10?
Negative 10, or mine is negative 10, 10.
Oh, okay, so you just had regular,
Yeah.
like Zoom 6. Fine. So there's your semicircle, looking pretty much like a semicircle. And then the parabola fits, well, pretty much fits the semicircle pattern for a while. Right? And then, of course, the circle is going to close back in on itself, and the parabola is going to stretch out its arms forever. So we don't expect them to fit the whole time, right? But for a while, for purposes of our lens, it seems to be the same path. In fact, if you go to your table, let's set your table starting at 0 and going by 0.5, that's fine. Look at the table. And the values produced are really close. If I have 1.5 for my x, I have 1.1, 1.2, right? If I put in 2 for my x here, then I've got 0.2 something and 0.2 something. The values are really close. And again, the question is, does it matter, right? So we're going to come back to that question in just another quick minute. We're going to look at what is the importance of a focus as opposed to the center of the circle. In the center of the circle, all of your points are coming in reference to one fixed point, and everything is the same distance out. In a parabola, you have a fixed point also, your focus, and then you have points that are based on a relationship to a line. That is, having the same distance from the focus and the directrix, right? So if I go out this distance, in my mind, I'm saying my directrix is right here. But if we happen to have a reflective surface on our parabola, something that's covered in mirrors or glass or mylar, if we have a reflective surface, the ray doesn't come through, it goes the other way. Does that make sense? Right? So again, if we say, well, I want to hit this point right here, instead of coming down the equal distance to where we would find our directrix, a reflective surface on the parabola would shoot that beam the other way. Does that strike a chord? Have you seen anything like that before, where beams are shooting out any old which way. Have you seen that before? Anywhere? Maybe. I bet you have. Do you think you've seen a Mylar or mirror-covered parabolic surface with a little something? Let's just, I got it from Autotech. So one of these actually has there's the big screen where it's hard to see. There's one that has the cap covering over the bulb, and then the cap covering is missing. And I'd like you to pass this around and just look and think. You see this huge beam of light, all right? You see a huge beam of light. How big is the light bulb in there? Comparatively, the light bulb is about this size, and you've got this huge parabolic surface, so that this little beam of light shoots out light, shoots out light, shoots out light, and not just in 2D, it's a 3D surface, and covered with these high-intensity mirrors, then it shoots out this huge beam of light, and you've got this tiny little light bulb, all right? So, we have the same thing with our flashlights, right? I mean, you've taken these apart before, right? So, let me give you some of these to pass around, and look and see, don't they have the same properties? Right? And look and see how small is the bulb and the reflective surface to say, I don't need a bulb this big to get a big beam of light, I just need a really good parabolic reflective surface. Now what else? I've given you lights, what else can you use? What else? What else has this application besides lights?
Satellites.
Satellite dishes, you're wonderful. What else?
Projector.
What do you mean?
The lens right there.
Right, you've got this nice round lens, and what else? Anything else? Have you done any kind of solar cooking? Have you seen solar cookers? Magnifying glasses? All right, so now we're going to see a short little video clip that would let you see what's happened when something is aimed right at the focus.
If Las Vegas was dangerous enough, the new Vdara Hotel at City Center on the Strip has a small design flaw. Or is it a flaw? It seems the south-facing tower is also kind of a giant solar collector, which then directs the sun rays into what's being called the Vdara Death Ray. If you're at the hotel swimming pool at the wrong time of day and season, it can actually singe your hair and melt a plastic drinking cup. Not to mention what it does to your tan. So why do I think a death ray in Vegas is even worth mentioning? Well, it's simple.
All right,
Nerd.
so we're going on to the next part, where there's someone who was actually a guest at the Vdara Hotel.
All right, so if I told you I'm sitting out by the pool, and it was so hot, all of a sudden, I could smell my hair burning, you'd think I was setting up for the punchline. No, this was no joke. This was an attack by the death ray.
That started happening, and then they laid down. I actually thought that, oh my God, we've destroyed the ozone layer, because I am being burned. And it wasn't until I ran under the umbrella and saw that there was no shade, that's when it dawned on me. But I could not understand why I was getting burned.
William Pinchas survived both his trip to Las Vegas and the death ray. He was laying out by the pool at the Vdara Hotel in Las Vegas.
I was sitting in my chair for maybe 30 seconds, and at that point my head was steaming hot. In fact, my hair felt like it was burning. I could actually smell my hair burning. And I'm rubbing my head. I felt like I had a chemical burn or something was wrong. I couldn't understand it, so I just laid down on my chair. And at that point, the back of my legs and my back started burning.
Now, the Vdara is an impressive structure covered with glass. Because of the curved shape of the hotel, sunlight is intensified and reflects directly at the pool. Thus, the death ray.
It was all bright. And that was when I looked up and I saw all the light reflection of the sunlight coming off of the Vdara and the Aria Hotel.
Temperatures in Las Vegas are often over 100 degrees, but it's estimated the temperature around the pool was 210 degrees because of the sun reflecting off the building.
All right. Yes, the weight run off the guess. We're going to look back at our telescope lens and try to answer the question, which one would take a better picture? Which one would focus the image to a clear spot? The spherical lens or the parabolic lens? The parabolic lens, the circle has no reflective properties. It doesn't have any reflective properties, but if there's an object far away that you're looking at, and it comes and hits the parabolic lens, it'll reflect back to one particular point, called the focus, and take a clear image. Those of you who have really nice cameras and you could set the f-stop, the F standing for focus. Just letting you know. But, and so we do have a clear image. And we're going to go to another video clip. If we were in a quandary about, gee, the graphs look identical, who's to know whether we should use a spherical lens, a parabolic lens, does it matter, everything looks the same, you might not have been alone. We're going to another application about the Hubble Space Telescope.
They could make that idea work, but at a price. They would have to select and sacrifice one existing instrument in order.
Hubble symbol.
Arrays speed photometer, and that 10 years before, but
Between cosmology. Hubble symbolizes man's quest for the bridge between cosmology and philosophy. And so when you go off to catch that thing and it appears on the horizon, it's a powerful moment.
The conclusion we've come to from that is that there's a significant spherical aberration appears to be present in the optics.
It's critical to look at how you failed. And it is inexcusable the way they failed.
10 years before, by a simple mistake with a measuring instrument, the mirror had been ground to the wrong prescription. If anyone at NASA had checked it, they would have discovered that if light striking the outside edge of the mirror is focused here, light from the inside edge would be focused in a completely different place.
All right.
So when they took a picture of a star, this was what it looked like. The best arrangement they could find was to
So we'll
fold.
stop at that one. That picture that they took, they spent millions, billions on the Hubble Space Telescope, shot it into space, wanted to collect a lot of pictures about, hey, how about those rings of Saturn, how many planets, how many moons are orbiting Pluto, and they got these grainy pictures back.